start with the introduction here for Paul. Paul Brasnett is with Imagination Technologies, a very interesting name, out of the UK. Comes a long distance for us. We've had a number of speakers from the outside. And what Imagination Technologies does is create and license a range of multimedia and communication processes needed to create systems on chips for mobile, consumer, automotive, enterprise, infrastructure, IoT, and embedded electronics. And Paul's involved with their PowerVR vision and AI cores. Paul himself has expertise in the area of image and video processing. And back a while ago, was part of the team that developed the part of the MPEG, one of the generations of the MPEG standard. So you have him to thank or complain to. Paul's going to talk today, combining with the last talked about image classification, and Paul's going to show us how image classification has now evolved to object detection in embedded devices using deep learning for computer vision.
Okay, so good afternoon. So yeah, so the kind of the reason for wanting to do this talk was really. So we see lots of interest from our customers in running deep learning algorithms for a range of tasks. One of the most common is object detection, but what we quite often see is that they're not necessarily making the best choices about the selection of networks or how they're choosing to analyze the applications. So you know, the purpose today is just to try and give a bit of insight into for kind of object detection. How what are the kind of choices and things you can look at for when you're targeting embedded market. So I'll give it a bit of an introduction in a minute to Imagination Technologies and the space that kind of we're looking in and set the context for this talk. And then I'll look at some kind of key object detection networks. And kind of look at how well they're suited for embedded vision or not, and then look at taking some of those and some optimizations that can be made to make those networks better suited, and then some summaries at the end. So, just to introduce people, so as the introduction said, so I work for a company called Imagination Technologies. For people who aren't familiar with us, we develop hardware and software IP. Typically licensing to semiconductor companies as part of their SoC design process. So I'm part of PowerVR. Within PowerVR, we kind of got a long track record, long history in graphics and GPU technologies, amongst other things. And more recently, we've been investing heavily in developing vision and AI technologies, both using our GPUs, but also dedicated hardware as well. We also have communications IP, so a part of Imagination Technologies called in Sigma, looking at Bluetooth, Wi-Fi, that sort of thing. Worldwide, since the company's been in existence for sort of around 20 years or so, over that time we've shipped IP in something like 10 billion units. And we're based in the UK, just outside London. So now kind of moving on, because that gives a bit of background to us and what we're doing. So yeah, as I said at the start, object detection is kind of seen as important by a lot of our customers. So we'll just look at some of the markets that people are interested in. So here's kind of it's a sort of a markety slide, right? But smart cities is kind of a concept where, you know, trying to embed intelligence throughout a city. And so there are kind of a range of different tasks within that. And so if we take sort of passenger controls in an airport as an example, so airports are now starting to move to a, so Heathrow, I think next year they said they're going to be rolling out a system whereby you don't need a boarding pass anymore. So you will, when you check in, your face will be recognized, and then as you go through the airport, they'll track track you, and you'll be allowed through the airport without having any additional checks. So a key part of that is face recognition technologies, and so a part of face recognition isn't a single algorithm, it's a series of algorithms. One of the first stages you need to do is to be able to detect the faces. You've got cameras around the airport. You need to detect those faces before you can do the recognition. So there's a key requirement there for large-scale object detection. And then another example is kind of public safety and traffic monitoring. So kind of monitoring traffic flows throughout a city. You need to be able to identify or to detect the vehicles, the classes of vehicles, and to be able to understand kind of and to manage the traffic flows throughout a city to try and make things as efficient as possible. And there's kind of a range of other things, and many of which are kind of built on the fundamentals of needing object detection as a starting point. And then kind of another use case is kind of this concept of e-cockpit, right? So in cars are becoming increasingly sophisticated in their use of technology. And one example of this is sort of driver monitoring systems. So within some safety certification around the world, they're starting to require moving to systems where you are actively monitoring the driver to make sure that a driver is paying attention. So again, being able to detect the driver is an initial first step to some additional processing to monitor the alertness and attentiveness of the driver. And then kind of as you move, kind of got autonomous driving there, as you move to kind of semi and fully autonomous driving, the ability, and there's a high need to be able to identify and track other road users around the car to make sure that the car is being driven in an appropriate way. So it's just kind of pulling out a few examples of where you need object detection. And there are many more that we see from our engagements with customers. And one of the key things is there are some use cases, like with fully autonomous driving, where you need very high performance. The latency requirements are very, very high. So you need very low latency, right? And you need to be very accurate to make sure you're not missing pedestrians or other road users. And there are other use cases where, let's say it's a camera in a fridge, and you want to be checking whether you're going to run out of milk in your fridge, right? The accuracy requirements there probably are significantly lower, and the frame rates required are significantly lower. So a lot of thought needs to be put into making sure that the right level of accuracy, the right level of performance is being selected for a range of different tasks. So if we go on to look at kind of the details of object detection networks, today there are kind of two fundamental philosophies that seem to be adopted for object detection networks. The first is kind of the two-stage networks. Things like faster RCNN is probably the most well-known of these. So from 4 years ago or so, but there are other approaches like RFCN and more recently mask RCNN, which allows you to do kind of more instance segmentation rather than just the object detection. So that's kind of one approach, is the two-stage networks. The other is single-stage networks. So that's kind of with things like YOLO with its various different versions, SSD, single-shot detection, and then more recently RetinaNet. And so there's kind of these two fundamental classes of object detection algorithms that are kind of gaining traction, and they have different advantages and drawbacks, which I'll kind of look at in a little bit. So if we look at two-stage networks, and I'm using faster RCNN as kind of a representative example of a two-stage network. So it kind of goes through, you kind of have these multiple different blocks. So feature extractor, so that goes from your input image down to some low-level features. That's then fed into a region proposal network to identify candidate regions where objects might be in your input image. Then goes through a non-maximum suppression, so to try and eliminate low confidence or high overlapping regions. Then goes into some ROI, region of interest operation, where the output from the non-maximum suppression, so the regions that are detected, are selected from the feature extractor, and those are then fed into the classifier. And so for every region that's detected from your region proposal network that goes through the non-maximum suppression, you need to run a separate classifier stage. And that outputs your object classification, and then typically a refinement on the exact location of your object. So if we look at the operations that are being performed, so the feature extractor, region proposal network are typically very convolutional neural network based. You then go into some quite different processing operations, so that you have non-maximum suppression tends to be quite a serial processing operation. And then the ROI, either pooling, warping, align, there are different variants of ROI selection, but those tend to require either a significant amount of bandwidth to read a lot of data, or they require some bilinear interpolation to select your region. So it's kind of very different to kind of classical neural network operations. And then you go back into a more traditional convolutional neural network. And just to point out, so again, this back end kind of runs once per region of interest. And what that means is you end up with a non-deterministic cost. So depending on the number of potential regions detected in your scene, you can end up with a very different ultimate cost for the inference of this network. And if we compare that with single stage networks, so here we're using SSD, single shot detection, as our example. Again, we've got the feature extractor, which we saw previously in faster RCNN. What we have here then is a kind of a multi-resolution classifier. So we're processing the features and downsampling and outputting detected objects and confidences for different regions, and that feeds into a non-maximum suppression. And so, again, if we look at the operations that are being performed, you see kind of a very convolutional neural network focused. So most of the network is very convolutional neural network based, and you have a relatively small amount of kind of serial processing, this non-maximum suppression at the back end. And just to contrast with another single stage network, so here looking at YOLO v2, it's something that has a lot of interest. We see, when we talk to our customers, some are very keen on SSD, some more keen on YOLO v2. So just to kind of compare, they're quite similar in their approach, but YOLO v2 does a kind of a single final classifier rather than the multi-scale classifier. And so here we've got some results. So this is kind of looking at, so we've got the kind of meta architecture, so the either single stage or two-stage network. So faster RCNN is the blue circles, RFCN is two-stage, it's a green circle, and SSD is our single-stage network is a red circle, and they're grouped by the different feature extractor network that's being used. So VGG16 is kind of a baseline, I would say. And then kind of MobileNet is a much higher efficiency version, or a much higher efficiency feature extractor. But just to kind of pull a few things out, what we tend to see here is that particularly for the higher complexity networks over here. We see that the two-stage networks are typically achieving higher accuracy. It doesn't necessarily hold true for some of so for Inception v2, we actually see SSD performing to a higher level of accuracy. But typically, we tend to see two-stage networks able to achieve a higher level of accuracy. And if we compare that with, so now we're looking on the vertical axis, this is kind of runtime on a GPU. It's not one of our GPUs, it's a NVIDIA GPU. And we've got different feature extractor networks, and then we're grouping here. So we've got faster RCNN, RFCN, and SSD. So it shows you the relative run times for the different approaches, two-stage or single-stage. And what we see across the board is that single-stage networks, SSD, are always faster. Another thing to note is kind of these black bars dictate or illustrate the variation in execution time. So it's kind of a minimum, maximum execution time. So you can see, with the single-stage networks, there's no variation in execution time, or at least nothing significant. With the two-stage networks, you can see some very significant variations in the runtime. So what we see is, just to kind of draw some comparisons and some points from this data, single-stage networks typically tend to be faster. They have this sort of deterministic execution time, and they tend to have much more what I'm kind of calling here kind of pure convolutional operations from end to end. You've got a little bit of serial processing for the non-maximum suppression, but by and large, they are very significantly pure convolution. They don't always offer so I've said performance here, really I mean accuracy. They don't always have the best accuracy, particularly on smaller objects. Comparing that with two-stage networks tend to have the higher accuracy, and they tend to perform quite well on small objects. But they do have this kind of scene-dependent execution time, and they have this very different type of processing in the middle of the network. And these mean it tends not to be well, two-stage networks tend not to be well suited to embedded applications. It's not always the case. There may be some cases where it is, but as a general statement, the single-stage networks tend to be much better suited for embedded markets. So we kind of looked at the difference between two-stage and single-stage networks, and our recommendation that single-stage networks are generally better for embedded markets. So we're going to look now at given us a single-stage network, how can you kind of tune and optimize that for your particular target markets and target applications? So generally, when you're kind of developing algorithms for embedded computer vision, or developing products, there's kind of a range of trade-offs, right? So the cost, the compute required, the bandwidth required, the power required, and those are typically competing against the level of accuracy required, the frame rate or latency required. And so a lot of the effort is in trying to detect or trying to work out what the right performance points to hit within this area are. So I'm going to look at a few key things to consider. One is the feature extractor, right? So choosing the right feature extractor. So as a baseline, we're going to use SSD VGG16. So the original single shot detection work was based on VGG16. So that kind of forms a good baseline in terms of performance, in terms of bandwidth required, in terms of cost to implement. Then we'll kind of look at an alternative network feature extractor that gives much lower computation. So MobileNet really helps to lower the computational load. And then if you want higher accuracy, you can use something like Brasnett 50. So we'll have a look at those and kind of the relative costs and benefits of those in a minute. And then we'll also look at there's kind of something that came along with the RetinaNet paper over the last few years is something called a feature pyramid network. And we'll kind of look at how those can be added to SSD and what that does to help improve the accuracy when you're really targeting high levels of accuracy. So here we've got on the horizontal axis is inferences per second. So the higher, the better, typically. And then we've got accuracy on the vertical axis. Again, the higher, the better. And then the size of the circles indicates the bandwidth required to execute these networks. And we've got 3 points here. So the baseline blue over there is VGG16. So you can see it's a relatively large. That means it needs a relatively high amount of bandwidth. So if we compare that with our with our MobileNet point down here, what we can see is MobileNet gives much higher performance. And performance here, I'm talking about inferences per second, so you can go much, much faster. All what you could do is for a given frame rate, you would need much less compute capability. So it depends what you're trying to target. And then it also, you can see, is smaller circle. So you need much lower bandwidth. And again, that comes really down to the system cost. And it's slightly lower accuracy, but it's a similar sort of accuracy to VGG16. If you're looking at something like Brasnett 50, what you see is you can achieve higher performance. And again, here I'm referring to performance as inferences per second. Lower bandwidth, that circle's smaller for Brasnett 50. And you're getting quite significantly higher accuracy. So by making smart choices about the feature extractor, you can kind of hit a range of different performance points. But we still see, when we're talking to customers, we still see lots of interest in using VGG16 as a backbone. There's no cases that I can see where it's a good choice. So then if we look at kind of, as I said, feature pyramid networks and how we improve accuracy. So I don't know if you can, how well you can see this, but so one of the key things is that to improve accuracy, context becomes really important. So with human vision, it may or may not be easy to see what that is. When you put something in context, so hopefully you can see it's that lady's hands, it becomes easier to make a judgment about what something is when it's in context. So typically object detection networks like SSD, they perform the classification at multiple scales, as we saw earlier. The higher resolution data, which corresponds to smaller objects, is extracted from earlier in the network. And so you lose you don't get the opportunity for low resolution information to be included. So what FPN does is gives a way for that information to be included. So kind of looking at this block diagram, so this was roughly how SSD looked some slides back. So we've got the feature extractor. We're now going through multiple resolutions. But here we've only got a single classifier, the lowest resolution. And then there are classifiers on the way back up. So between the low resolution, you're doing an upsampling and running the classification on the combination of the high resolution data and the upsampled low resolution data. And so that allows it to bring in contextual information to make that final decision about what it's looking at, which then feeds into the non-maximum suppression again. So you kind of increased the size of the network, but you're getting better accuracy. So if we kind of see how that looks, again, taking this dark blue, so again, inferences per second, accuracy. So here we're actually looking at object detection accuracy. So VGG16 is our baseline. And if we compare VGG16 with the mobile net with an FPN backbone, here we're running at a somewhat higher resolution than we are for VGG16. But what we see is we can get higher performance in terms of inferences per second. You can get lower bandwidth, so the circle is somewhat smaller than it is for VGG16, and you get higher object detection accuracy. And where that mostly makes a difference is really on those small objects that you weren't able to detect with without the FPN feature. And then, if we compare adding FPN to not having FPN, you can see significantly higher accuracy. A key thing to note is that the resolutions here are different between the FPN and non-FPN version, and so there's potentially trade-offs that can be made to select points along a curve between these two. So the kind of the key messages from the presentation that I've been doing is really single-stage object detection architectures are kind of really good for embedded vision applications. The selection of the feature extractor to match performance and accuracy requirements is really important. You don't want to necessarily get overly high accuracy for some tasks. You may want to minimize cost, but making sure you get the right level of accuracy is really important. And the feature selector is a really important stage in that. And if you really want the highest level of accuracy, FPN feature pyramid networks can really help to achieve that level of accuracy. So just some additional links here. So there's a good paper from Google on some of these aspects, kind of the speed accuracy trade-offs, and some other links there. And we've got some of these networks running on our booth. So if you want to come and have a look and have a chat, please feel free to pop by. Thank you.
Thank you. Can we have time for a few questions before the next speaker here? I was just wondering, do you have some type of problem you found that the single-stage network just totally blows away the two-stage, or is it the opposite?
The big thing is the efficiency, right? So you can run things at a much higher frame rate, or with much lower cost with the single-stage networks. The two-stage networks, yeah, you just end up with higher cost. You have to invest more to get a similar sort of return from them.
Okay. Again, if you have questions, please come up and use the microphones in the middle. And what about your hardware? Since you're a hardware supplier, how does your hardware apply to?
Right. So as I said, we have examples running with both single-stage and two-stage networks. So the single-stage networks are running on dedicated neural network accelerator hardware, and so those map really nicely. The two-stage networks, you've got this kind of additional processing in the middle that maps very nicely to our GPUs. So it's kind of combining the dedicated neural network processing with some other processing in the middle.